So, to get on to the lecture content for today we have 3 learning objectives for you, things we want you to master after this lecture and after we've practiced this a bit. We want you to be able to identify use cases when we want to use this PriorityQueue ADT. We want you to be able to describe the invariance of this heap data structure and explain the relationship to the runtime of their operations. And we want you to be able to understand how you can use these remove min and other operations that we'll talk about on this heap structure. So we're going to start by overviewing what a priority queue is, and also in this video talking a bit about some ways that we might already know how to implement this using the structures that we've already heard about. And then in later videos, we're going to talk about this new data structure called a binary heap. So an important use case for when we might want to use this thing called a priority queue. So imagine you're managing food orders at some restaurant, maybe some restaurant in the hub at UW. And we talked about back way in the beginning of the quarter in lecture 2 that you might use something like a queue to keep track of who came in first. Now suppose Anamari Kause walked in, and because she is the president of the university, you probably want to serve her earlier than later so that she leaves a good Yelp review. And so there might be some context where you might not want to serve the first person that came in. Maybe each person has some priority, and you want to serve the person with the highest priority first. Now, and maybe other people can have differing levels of priority. So maybe your CSE 373 TAs can have definitely less priority than Anamari, but maybe more priority than just any random person. And so there's this notion of maybe assigning each person some priority that you want to help them with. An analogous example that's not favoring people at UW is thinking about hospital care. So usually when you're thinking about the emergency room, maybe you want to make sure that someone that has a high priority injury gets served before someone that has a tummy ache. And so this notion of each person in line might have some priority of who we need to help first is this case when we want to use this PriorityQueue ADT. So what is the PriorityQueue ADT? You should think of it a lot like a queue. It lets you add people at the end and remove people from the front, but these ends and fronts are going to be a little bit more washy now. Instead of doing a first in, first out approach, we're going to order all of the elements by this notion of priority. And the priority is something you can decide as the designer or the user of this ADT. So you determine what element is the highest priority. But we're going to have a lot of the behaviors, or at least at face level, that are similar to a queue. So you're able to add values, but instead of having a remove that removes from the front, we're going to have a remove min, and that's going to remove the element with the smallest priority. One thing I'll mention, I'll talk a little bit about on the next slide. Kind of confusing. By convention, we think about the highest priority element as being the smallest element. It's just something that we picked up from Java in particular. We'll talk about this as just a design decision of which one you want to, the semantics of what these calls mean. But when we talk about the minimum element, we always mean the highest priority one. And then peek min also lets you peek at that element that you would remove. This ADT is used all over the place in computer science. If you took CSE 143 here, you actually saw what a priority queue in our Huffman coding assignment. It was the last homework assignment of 143. It's also going to show up a lot of times in future weeks of this course when we talk about sorting algorithms, and also when we talk about these things called graph algorithms. A graph is essentially a social network. And whenever you want to do algorithms on them, a very popular type of algorithm uses this PriorityQueue ADT. You can imagine a lot of places that you would want to use a PriorityQueue ADT. I already talked about running a restaurant or running an emergency room, but you can imagine even more pressing issues require priority queues. So you can imagine the Husky coronavirus testing program where they have everyone on campus, faculty, staff, and students sign up, and then they randomly select people to be tested. Now, I actually don't know how they're implementing this behind the scenes. You can imagine they're just doing a completely random sample. They probably aren't, though. They're probably assigning priority to people, maybe people that are showing some symptoms or recently contacted someone that had symptoms, or maybe they're in a high-risk group or a group that's more likely to contract the virus. And you might imagine assigning each person some priority, and this priority function could be really, really complex that captures all of the things about health that I, a computer scientist, don't understand. But if they can assign priority to them, they could just stick everyone in a priority queue and then pull out if they have resources for 200 tests, they could pull up the 200 people with the highest priority. So this PriorityQueue ADT is used all the time places. Now, one thing I mentioned briefly earlier was this idea of a bit of semantics issue here. When we talk about priorities in the class, we're always going to be talking about minimum priority queues, meaning that we always want to return the smallest value whenever we talk about remove min or peak min. So we're going to define smallest value as being highest priority. But you could just as easily talk about a maximum priority queue that always returns the maximum element. They're the same structure. You could just negate all of the priorities and you can turn one into the other. But one thing that's required here is this notion of items being comparable, meaning that you have to be able to say, is this object less than this other object? In Java, this always comes by implementing the comparable interface. But in theory, you just have to have elements that are comparable to one another. And again, we're going to always talk about this min case, but it's always good in the back of your mind to think about, oh, max is also something you totally could do. It's just different semantics here. So what I want us to do for the rest of this video is talk about some ways using the tools we already know to implement this PriorityQueue ADT. You can already kind of imagine maybe, okay, well, if it's a queue like structure, it's probably going to be like it could be a linear structure, like some array or a linked list, and I store things in sorted order. And then I could do operations on that structure. This is what I was mentioning why priority queues and this new structure heaps are that we'll talk about in the next video are one of my favorite topics in 373, is because we're going to see this kind of whole strain of non-obvious jumps to come up with a very clever solution that implements this problem really, really well. So I really like the twists and turns that this story provides. But first, we're going to talk about the tools we already know and how we might actually go about implementing them. So I would argue, already have tools to get perfectly fine implementations of this PriorityQueue ADT. So here are 3 different implementations that you might consider. For one example, you might consider an unsorted array. What I mean by that is when we're adding values to it, we're just not going to order about structuring the data in any meaningful way. We'll just use an array, add things in. And then when we want to remove min, we could do something like scan through the entire structure, find the minimum value, and remove it. Same thing with peak. We just loop through, find the minimum value, and return that without removing. So that's one implementation. It's in some sense the simplest. It's doing the least amount of work to maintain structure. You can imagine, though, another implementation would enforce a little bit more structure. And so just for example, I chose a linked list implementation for the second one, where everything is sorted. So we are going to sort the nodes from smallest to largest. And then when we add values in, we add them in sorted order. And then when we remove the smallest. And you can imagine, oh, well, if I'm using this sorting property, maybe I can use something like an AVL tree here, where AVL trees have this notion of sorted order. Maybe that would help me out a lot when thinking about how to do these operations. So let's walk through and say, okay, if we're using each one of these, what is the runtime of these various operations? So for example, if I'm using the unsorted array that I just described, how might I implement add? Well, if I don't care about the order of the data in the array when I'm putting it in, because I know my remove min is going to go through and find that smallest element, I just need to add it at the end. And I have on the slide here, just for example's sake, let's assume resizing is not going to happen. So in that case, we just stick something at the last available index. And so this runtime for add, in the worst case, is going to be theta of 1. Right? We just go to the index, add it there. Okay, what about this doubly sorted linked list? Oh, doubly linked list that's sorted, sorry. One thing I should mention is in this implementation, let's assume that we have a reference to the front and the end, which is usually the case for doubly linked lists. So we have a reference to the front and the end. Now, how would I implement add here? Well, I can't just simply add it at the end, because I'm saying here that I want my list to be sorted. I need to sort values from smallest to largest. So if I want to add a value, I'm going to need to search through the whole linked list to find the right spot to put it, right? If I have the numbers 1, 5, 10, and I want to add the number 4, I need to go through the list and find the right place to put it. Now, unfortunately here, this is going to end up being an O of n operation. Because in the worst case, I might have to add something in the middle that's an index around n over 2. I might have to scan through the whole linked list, and so I will have to scan through n things. So here it's going to have this O of n operation. What about the AVL tree? Well, if I'm going to add a value to the AVL tree, you might remember that AVL trees maintain this AVL invariant that leaves them roughly balanced, which ends up giving us this nice log n runtime. I'm spelling with my finger right now, so I'm trying my best. It's going to give us this nice log n runtime. Okay. Now, the challenge is, with these three structures, how do I implement the other methods? And how do I actually go about computing their runtimes? So I want to give you a chance to exercise this. I want you to think about the peak example. So think about the peak method, and what do you think, how would I implement this? And then what is the runtime of that implementation? In this question on item pool, it's a free response. All I'm really looking for are the actual runtimes for peak, so just say what the 3 runtimes are. But it's important to think about how would I implement this in this structure as I described it. So take a second and think about what are the runtimes for the peak operations using these different implementations. Okay, so hopefully I had some time to think about that. So here I would argue for peak, what we would end up doing for an unsorted array, well, I don't know where the minimum element is. So I'm going to actually need to go through the whole array in the worst case to find that min element. What about that doubly linked list? Well, this case is going to be different. I don't need to search through the whole list for the smallest element because I know the list is sorted. The way we implemented this would be that the sorted thing would probably be in the front. And so when you want to peek, you already have a reference to that first piece of data. And so here we'll end up with an O of 1 runtime for peak, which is a property we really, really want. Now, what about the AVL tree? How do I find the minimum element? This is a little trickier method to implement. It turns out that we can always find the minimum element by essentially going as far to the left as we can in our AVL tree. If you always go left, 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 left as far as possible, this is going to show you the element that's smaller than every other element. And we argued, just like with add, that this runtime ends up being log n, because at worst case, let's put an O there, this ends up being something like log n height. Okay. Now for removing, it's going to be a very similar story. For the unsorted array, you would have to search and remove. That searching is still a big theta of n operation, but the removing is an additional big theta of n operation for the unsorted array. For the doubly linked list, if it's sorted, since we're just going to remove the thing at the front, this also ends up being O of 1, which is not too shabby. And with the AVL tree, this one we did not talk about in class, but the remove operation for an AVL tree is going to end up being very similar to addition. It's a little bit more complex in terms of how you update the tree, but I'll just tell you here that just like the add method, it's going to be log n. It's going to have to do something potentially only to the height of the tree, which is bounded by log n. So I'm going to go ahead and clear this and advance to the next slide that shows all these things. So here are 3 implementations, and you can already see we could use our design decision tools to figure out, well, which implementation do we think is best? The unsorted array has very fast addition, assuming you don't resize, but removing and peeking take a long time. While the doubly linked list that's sorted is kind of the opposite. Adding takes a long time, but removing and peeking are very, very fast. And then the AVL tree is not constant time for any operation, but it's better than linear time for all operations. So it's kind of like in the middle in some sense. Now, one thing I'll mention is that you can be a bit cleverer about this, which is instead of just storing the unsorted array or the doubly just the list, we could theoretically keep track of extra state to help us track where this minimum element is. So for example, if we wanted this priority queue to have a fast peak, we might want to store an extra field that always references what's the smallest value so far. Now, this is a very simple improvement to make. It's just adding one extra field, and it hopefully should only encourage constant runtime to update it whenever you add a value. So for example, you could say for the unsorted array, you store an index field for where the minimum index is. And whenever you add a new value, you just compare against that and update. All of that would be constant work. So now, once you know that index, peaking is really fast. Removing for the unsorted array, though, is still big theta of n. The reason is, even though we know where that minimum element is, we still have to shift all the other elements over. So it's still going to be that O of n, or big theta of n business. Doubly linked list, this doesn't really help us out at all, so it doesn't really matter. But then for the AVL tree, suppose, for example, you just kept a reference to that smallest node, then you could just return its value right away. Removing is still going to be that log n, because you might have to restore the tree for the AVL invariant, but we could do that. So there's a bit of a better implementation here, what we're all talking about, where we just keep track of a little extra information. But what I want to argue is we are going to use a completely different data structure, one that's going to look really wacky the first time you see it, but actually helps us implement this idea of the priority queue really, really well. But we're going to talk about this thing called a heap in our next video.